In this video, we're going to derive the pullback or vector Jacobian product rule for scalar root finding. You can think of scalar root finding as a wrapper to a numerical algorithm that takes an optimality condition, or here in that sense a function, and solves for its roots. This function is parameterized with a value theta, which changes the positions of the roots. So it is also an argument to the wrapper to our function. So this function takes the parameter theta, then evaluates the numerical algorithm and returns the root x. The task of the pullback or the vector Jacobian product is to backpropagate cotangent information. So we have to backpropagate cotangent information that we have on the output, which are x bar, which is another real valued number, to the input of our function, which will be theta bar. This could then be part of a larger computational graph in which you have a scalar root finding and you want to obtain gradients with respect to some loss functions. And the crucial notation here is that we want to do that without reverse mode AD through the solver. So without reverse mode AD through the solver. And by through the solver, I mean applying the rules of reverse mode automatic differentiation to all the operations that are part of the algorithm. So for instance, some multiplications or some divisions, some subtractions. Typically, this is also called unrolling or piggybacking. So unrolling or piggybacking. And that's not what we want to do. Rather, we want to step over the numerical algorithm by employing a result from the implicit function theorem. In general, what we want to do is to obtain our theta bar by multiplying x bar with the derivative of the function over which we want to propagate derivative information with respect to its input. And just recall that this df by d theta is another real valued number. So in that sense, we are just scaling the x bar to theta bar. And also note that df by d theta is equivalent to dx by d theta if you correspond the function with the output of it, which we named x here. Well, how can we do that? The idea is to use a result from the implicit function theorem, which we can obtain by applying the total derivative on the optimality condition, which was given by the function g. So let's take the total derivative of the optimality condition. So the optimality condition was the function g, and do that with respect to the parameter theta. So dg with respect to d theta is essentially partial g with respect to partial x, and then partial x with respect to partial theta, because we have a nested dependency. Obviously, the solution to the root finding algorithm will be x, and if you change theta, you will most likely also get a different x. So x has some sort of a dependency on the parameter theta. And then of course we have the explicit dependency of g with respect to theta, so we will get plus dg with respect to theta. And this has to be 0, and that is because our optimality condition evaluated at the concrete x and theta value that we have here. So after solving a forward step where we get a concrete x for a concrete theta, has to be 0. Otherwise, it would not be a root to a function. And if we evaluate the total derivative at a position where it is 0, this total derivative is also 0. And informally, you can think of that as if there is nothing, then also nothing changes. The total derivative that we just took helps us in order to identify the dx by d theta. That's the quantity we are interested in. Essentially, this is the quantity or the scaling factor with which we want to scale our x bar in order to go to theta bar. Let's rearrange for that quantity and see that dx by d theta is essentially minus dg by d theta divided by dg by dx. And we can do that because those two are of course scalar values. So let me quickly note that down. This is a scalar value, and that one is also a scalar value. And with this derivative found, we can plug it back into the general definition. So plug back into general definition. And then we get that theta bar is x bar multiplied with minus dg by dx. And I will put d to the minus 1 here in order to indicate that we divide by it, multiplied with dg by d theta. Well, and with that, we have found an expression for theta bar. So then we can write down the full pullback rule. So the backward rule on our wrap to the numerical solver f evaluated at the primal theta, and the cotangent on the output given as x bar will be that we first, of course, call the original function on theta, and this will yield the output x. And then we have, as the backpropagated cotangent information, minus x bar, and then dg with respect to dx in brackets inverse. So you could do 1 over that because it's a scalar value, and then multiplied with dg by d theta. Then let's close that down. This is our backward rule, or let me also indicate that one here. This is our theta bar now. And that of course leaves open the question, how do we obtain the dg by dx and the dg by d theta? Since we assume that the function g is automatically differentiable, we can get those in terms of a reverse mode autodiff approach. And this is how you would do a backpropagation over the solution to a root finding problem without stepping through the solver or without unrolling the solver iterations. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. Here you will now see similar videos, and I hope to see you in one of the next videos.